Alright, hello class. This is Miss Riggins coming from you from the classroom. Finally got the mic working, yay for me. Anyway, we're going to talk about today applications of polynomial functions. Now, we have been working with polynomial functions for a very long time, but we really haven't looked at how they're used in real life situations. Well, there are many physical and business situations that can be modeled or described by a polynomial function. And the significant values of this polynomial function tell us important information that we can use in these situations. So what are these values? Why are these values so important? Finding the values of the zeros of a polynomial also can indicate what the beginning and ending times of if you have a graph that is time versus distance. So the zeros begin when the situation started to when it ended. The y-intercept can be also the starting values, and the local max can be the highest value in a region, and the local min can be the lowest value in a region. And if I actually have the function that models the situation, I can actually plug in different values to be able to make predictions that may not be part of my data. So how do we come up with or determine the polynomial function to use? Well, that's where polynomial regression comes in. We're given a scatter plot, or we can maybe given a bunch of data, we scatter plot it, and we see, hey, the graph of that kind of looks like a quadratic, or kind of looks like a cubic, or kind of looks like a 6-degree polynomial. And how do we know it? Well, if it turns 5 times, you remember the turning points of a graph, then that lets us know that it could be a degree 6 polynomial. So let's take a look at an example. So here we have a graph. The data is in blue, the scatter plot of the data, and when you try to connect the data points, we see it ended up being not smooth or anything like that. So then they fitted it with a polynomial function, and basically you can do that with the calculator. We're not expecting you to do that by hand, and in the calculator you can find the regression based off the type of polynomial that it is. So if this was a linear function, we do a linear regression. If this was a quadratic function, we do a quadratic function. In this case, it is a polynomial function, but how many degrees do you think it would have? Well, over here we see this could be a turning point, 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 this up here can be a turning point, and this could be a turning point. So we have 1, 2, 3, 4, 5, 6 turning points. So that lets you know that at most we can have a polynomial of degree 7. So I could have tried and fit this with a 7-degree polynomial because of the number of turning points I have. Or I could go down a little bit lower and say, well, hey, this doesn't really look like a turning point, or maybe because this data is so screwed right here, this could have been a problematic point, so I'm not going to consider that, or I'm not going to consider that, and we can eliminate that. But again, these are based off predictions, so there's no one correct right answer when you have a scatter plot of data. But we do have a polynomial that basically describes or fits this data. Not all the data points, but it does fit through most of the data points. And we can use this polynomial to predict future data values based off the function that it gives us. So here we have another set of data, and actually this is very interesting since Super Bowl just ended. This is a graph of percentage wins versus time. And what they do is they want to see, based off of the teams that drafted a quarterback, how many in the NFL draft, how many years did it take for them to get to a winning percentage? And so what they did was they looked at the data points and they predicted by fitting it with a quadratic. It looks very quadratic. They fitted it with the quadratic equation to predict how many years it would take to reach at least a 50% win ratio. So based off this graph, the prediction and the actual data looks to be pretty much the same. To reach its highest value, i.e. the maximum, or even the local max, it takes around 4 to 5 years in this particular data to be able to reach a winning percentage of over 50%. And then if I fit the data with a polynomial equation, I can figure out when will they get to no wins if they keep the same quarterback? So somewhere down here, based off the data, probably around year 12, they won't be able to win any games if they keep the same quarterback for 12 years. And those of you in football know that's not really possible. I don't know. But anyway, so what are we going to be doing in class? That's what you're interested in. We're going to be trying to find a polynomial that fits the data, and you can use that in the calculator. Or we'll be given a graph and trying to come up with an equation for the polynomial. And the best way to find the equation for the polynomial is by using the significant values. So here we have an example of a polynomial function, and because it turns 2 times, that means it's a cubic. And we're trying to come up with an equation that will describe this polynomial. Well, one of the things that we notice is that we have an x-intercept, or a 0, at -3, at 2, and at 5. So when we write up our equation, we know that since it has 3 x-intercepts, or 3 zeros, it has 3 factors. So since the 0 is at -3, then the factor is x plus 3. Since the 0 is at 2, then the factor is x minus 2. And since the 0 is at 5, then the factor is x minus 5. But if I were to just use this exact formula, I wouldn't be able to get the y-intercept that's down here at -15. So the a, which is the number in front of the leading coefficient, what number should a be so that when I substitute in 0 for x, I get -15? Well, in order to find that, that's algebra. So we substitute 0 in for x in each of our factors, and we come up with -15 is equal to a times 3 times -2 times -5, which is, of course, -30. So if -15 is equal to a times -30, then that means a has to be equal to -1/2. So now we have an equation that will describe this graph. And that equation is -1/2 x plus 3 times x minus 2 times x minus 5. And as you can see, since it is a degree 3 polynomial, it has 2 turning points, 3 zeros, and it has a local minimum at this turning point and a local max at this turning point. Okay, that's it.